Hi, everybody. JC here. We're having a little discussion with Dave in Peru, who's over there, and we've got Vivek and Eduardo, a few other people coming in, and Dave's got something very interesting to show us. He's been doing some experiments and working on the capacitors for the Magrav unit, and discovered something very interesting. How about, Dave, we go into the history of why you started doing this in the first place, and then we can go into why or what we actually did to correct the problems.
Hi, everybody. Well, Vivek in Singapore gave me the confidence to go forward and make capacitors the way he made them. And he had a working machine. And therefore, I was following positivity. And when you've got positivity, that gives you confidence to go and make something. And Vivek, if you can come in here, I was following your capacitors. I didn't even know what capacitors were used for. I didn't know anything, but I knew you had a working machine. So therefore, if I followed what you did, I thought that I would get a working machine, and I got one. Thank you very much. Vivek, or Max, whatever you'd like to be called, from Singapore.
Yeah.
Come in.
I'm here. Yeah, the thing about my Magrav's unit is that, like you, I also had problems with the capacitors because they were quite finicky in their construction, and my level of workmanship is not exactly very good. So the thing is, right now I've had to go back, take apart the capacitors, and start to troubleshoot the unit that I made itself. So I'm still in the midst of doing that. I'm very keen to know what you have done as far as the capacitors are concerned. How have you addressed the problem?
Well, isn't it funny? Because what I did was I did what you did, and I sat it on the desk and I went, what is he doing? I'm like trying to brainstorm what you're doing in Singapore. And I'm also speaking to John Carl in Canada. And I'm going, what are you talking about, John Carl? What are these things for? And then we've got the MIP Peru room where we've got Don Greenfeld and we've got all these other great people who are working with the same system that we've got, and they say, hey, I tell you what, take the capacitors out, you don't need them, and all this bullshit. Then I go up to John Carl and I say, John, look, you're my main supplier of information. Why do we need capacitors for these units? So John Carl, please tell us why we need this result that I've got here for you today. Why do we need capacitors, John?
Well, the capacitors are primarily a smoothing device, from what I understand. Now, clearly, my understanding is not complete by any stretch of the imagination. I still have a lot to learn. But what I understand, when we put the capacitors on there, it levels out and stabilizes the output of the device, so that it's not affected so much by the environment, by emotion, by the kind of load you put on it. It just makes it a little bit less sensitive, increases the efficiency slightly, perhaps more than slightly, but it levels out the output a little bit better.
Okay, so anyway, we had a discussion yesterday, John, and we said, I tell you what, let's do some twinking with the capacitors. And then lo and behold, right in front of my face, the solution happened. And Daniel's here. Hello, Daniel.
Yeah, I think I'm here.
And
some days I'm not, mind you, but I just look like I'm here. That's the other.
so right in front of my face, I made the first capacitors, which was a mistake. But then what I did was I put all the problems that you fellas told me about, and I put them on the table, and would you believe it? It showed up in front of my very eyes.
Okay, so let's
And
clarify.
that is the
Let's clarify for the audience. And what we're talking about here isn't a change in the design of the capacitors. Okay, what we're looking at is a way to put them together. 'Cause that's been a very difficult thing for a lot of people, is getting them put together properly so you don't damage your nano coating, your wires don't get messed up, they don't short out. There's been a number of people that have had pops because they didn't quite get them wired properly, or the capacitors weren't really dry. But the design, the pin in the center with the paper wrapped around it, with a coil wrapped around that, all nano coated, that hasn't changed. What did you do differently this time, Dave?
What I did was I made a mistake, and I love these mistakes. What I did was I built the first one with paper, and you know I've got a good system with paper, John Carp. I've got this, I can hang them up to dry up on the roof, and I've got this bone dry piece of paper that that comes out, and it's absolutely bone dry because it's been in 44 degrees of sun, 110 degrees, whatever you're working on, Fahrenheit. But then I accidentally built them without paper, and this is when I got resolved. Look at this. Now look at this. This is the big secret.
Well, that's not really the big secret. The secret is how we're hooking them together.
Yes, you've got it, John. Now, I can nano coat that, and I can nano coat that. Then I can put the paper on that, and then I can, with a bit of fiddling, I can put the paper on and drop that in there. So basically, we've got two nano-coated elements, one that needs paper after the nano-coating, and you've got no stretching, twisting, curling problems with nano-coating. This is the solution. John Carl, you can draw this on a piece of paper.
Mm-hmm.
Let me show you again. There you go.
Well,
okay.
what we need to highlight, Dave, is your connections between the three on each end, because that's really the secret here.
Say again?
I say what we need to highlight is the connection between the three capacitors on each end. That's the real secret. I mean, everybody knows that you make 3 pins and 3 coils and put them together. That's not a big deal.
Yeah, in fact, the way that you're showing right now, Dave, is the way that I'm doing it as well. So I want to see where the difference is in your connections, because that's where I believe the secret is.
The secret is the paper. The paper is the Gans linked paper, goes in the middle of these 3 pieces of coils, which is connected with, let me show you.
There we go. There we go.
And you've got a...
This is a
You got
connection system. Yep, yeah, we could see that actually pretty good. This is a connection system that was developed by Armand, originally to connect the layers of the stacker together to make it a modular system. Now, when I was discussing this with Dave, he brought the idea up, and what I suggested was to solve a problem that we have with a T connection within this capacitor array, was to make a coil that one end of it can handle 2 thicknesses of wire, the other end of the coil is only a single, as you can see in the center there. And we'll have to adjust, we'll have to tweak that design a little bit, but that appears to be working really, really well. And, oh, go ahead, Dave.
Yeah, no, it's beautiful. And what we do, I've made a jig in the workshop down in the shop here, and what I've done is I've thundered onto the table 2 sides and a piece of wood with 2 sides about 9 inches apart, and I've thundered through a couple of holes that can take the copper, and then you can wind. So you can either put 2 strips of copper or 1 strip of copper, and then you can wrap around. And then I make a 9-fold wrap around 2. Let me show you closely here. That bit there, right there. So you got 9 folds around 2 pieces of copper, and then we go to a single copper here. This is 9 folds around 1 piece of copper. Do you understand that, John?
Yes, I do. I most certainly do. It's a modular system. It allows you to simply plug your capacitors together. And it's a very, very simple system. We found in experimentation that using a system like this solves a lot of problems. It's very convenient, and it's very easy, and it works very well.
Well, what I found when I didn't use the paper was this. This is the big key. This is the big secret I got today, was look at that.
Yep.
You can nano-coat that, and you can nano-coat that. You then put your paper on these 3 elements here. You are not damaging your capacitors by spreading anything. And all you do is you build a little piece of wood or something. Eduardo in America, you will know how to do this. You just put a sheet of plywood, very thin, like the thinnest you can get. I think it's about 4 millimeters. And you drill your holes, and you can now grab hold of these joints, and you can put your zip ties through these joints, and you've got a real solid set of capacitors, which our engineers in Peru, Carlos, Flores, Roosevelt, and Jules, and Hector, all didn't like my capacitors. And isn't it funny that they didn't like something that I didn't like? So now what we've got is something that they like. And when I show them this, they're going to be very, very happy.
Yeah. One of the issues that came up in a couple of meetings, a couple with the manufacturers and with some private individuals, is when you make these capacitors, or even when you connect your coils together, when you manipulate that nano-coated material, you're causing damage to the material. You're scratching it, you're cracking it, you're crushing it. If you wind up with a matter-to-matter connection in there, after the nano-coating, your system won't function properly. It'll light up a light bulb, but you'll get no plasma out. You have to have that excellent, undamaged nano-coat layers brought together in order for this to work properly. So this is why Dave was concerned about this, because we had some issues with some of Dave's systems not operating the way they're supposed to. And through a few meetings I was involved with, what came out was the capacitors are the weak point. That's where things are going to fall apart, if they're going to fall apart at all. And the reason for it being, when you try to assemble these capacitors, particularly in the old way we were doing it, you're introducing damage into your nano coating, which you go back with a paintbrush and you paint some caustic on there and you hope it rebuilds. If we can make the system as modular as we can, so that it's pretty much completely assembled when we nano coat it, that eliminates that damage. And we should have a far higher degree of systems without flaws if we start working on it that way. Another thing, not to belittle you, Dave, or any of that stuff, but Don Greenfield, you had a lady speaking about the capacitors, and do you see? You put a little thing in the Skype chat earlier about mounting them around the unit. Do you see this assembly method as a way that would work very well?
Well, this is all coming from John Crow, a friend of mine that lived in town with me. And when he got her to look at this, she could see the energy field was going off to the side. It got pulled over to the capacitor, and it was swirling. And she said it was just going over. She said, "This is something wrong with this thing." He said, "It doesn't like it like that." He said, "If you're going to do anything with it, put a capacitor around the 4 capacitors around the coils equally." He said, "It balances the toroid field. It makes sense in theory." And John went one step further. He got thinking, well, he arranged it. He did it that way. He unhooked it completely, and he saw that he could feel that it was still working after she left. And he said, well, why do we need capacitors? Because Keshi doesn't have capacitors in his materials he sells, the kits he sells, or the Magrav units. So that's why we were rethinking. I unhooked mine, and it seemed to work fine. Maybe after the fact, after the mission is complete. It's been running for 3 months with capacitors, so maybe I still need with a new one.
All right. So yeah, if you're looking at doing it that way, mounting your capacitors around the periphery of the stacker device itself, this coil type connection system appears to be a really good way to be able to manipulate them. Give a little extra space in there. You can set it up in a completely different way. And again, like I was mentioning earlier, it eliminates a source of error, which is damaging that nano coating when you make your assemblies.
Yes.
Yep.
We lose you, Dave? Oh, Dave's muted. Anybody else? Anybody got any insights, any ideas?
Listen, John. I mean, that is the great question. Okay, Don Greenfield says, I've got a unit that's got no capacitors. So therefore, why should I spend time on creating a system whereby I do not damage my capacitors by putting them together? Basically, that is what I've designed, and I'm very happy about it. But Don Greenfield says I don't need capacitors. So where do we go to get information to say that I do need capacitors?
Well, we'll have to look at the two systems. We'll have one person set up a system without capacitors, one setting up ones with capacitors that we know are in really good shape, that work properly. And over time, we'll have to record the data, the nano coating, the reductions that they see, and we can get data to answer the question. Right now, intuitively, what I see is, yes, the system will work without capacitors. It's going to work better if you get the capacitors in there and working properly. Now,
okay, so can we confirm that that is just your idea? That is not, in other words, Don Greenfield has got a system working without capacitors. Therefore, that's his idea. And therefore, we need to merge these ideas together and say, Don Greenfeld is correct, and John Carl is correct, and Dave Stewart's correct in Peru. We've got a system where we're using the 3 bobbins, as I call them, bobinas, and then we've got 3 capacitors. Don't forget, we've changed our capacitors in Peru from 3 on the input to 3 split ones, which are Vivek's ideas. He had 3 split capacitors on his output, and we had 3 capacitors on the input. Now, what we've got is Don Greenfeld is telling us no capacitors. And what I'm saying is, I'm still persisting with the capacitors because I'm going to have 3 on the in and 3 on the out. I don't know if I've got a better machine. I cannot tell you. But Vivek, can you tell us, do capacitors work?
Well, the original blueprints themselves do call for capacitors. So there is a reason for the capacitors to be there. The other thing I want to mention is that the split capacitors I put on the load side originally is because in one of the teachings, Mr. Cash did mention to take part of the output of the load side capacitors and feed it back into the bottommost coil. So that's why I had split capacitors over there. Now, as far as the construction of my capacitors is concerned, I've got the same design as you, Dave, what you've demonstrated just now, where the capacitors are put together first before they get nano-coated. The only difference is that they are not modular. In fact, let me just grab my capacitors. I can show you.
Interesting.
Yeah.
Okay, here we are. These are the capacitors that I made. This is on the load side, on the grid side. So as you can see, like Dave, you know, if I were to straighten this, I would just be able to pull them out. Okay, I'm not going to pull them out all the way because the papers are falling apart right now, but for all intents and purposes, the central pins stay onto this side, whereas the springs stay onto this side. They are not modular in design. They are all fully assembled, but they are fully assembled before the nano-coating occurs. So the only difference over here between this design and what Dave showed is that Dave's is modular, meaning you can make all of the separate components separately, and then just before nano-coating, you assemble everything together, which I think is a much more elegant solution than this. This is very finicky.
Yeah, something that we need to address as well, just for informational purposes, is in a number of the other types of systems, the Gans collection primarily, we're seeing there are slight differences between where you are on the planet. In Singapore, the salt concentration is different than it is in Canada, or in where I am in Canada. If I use the same salt concentration Vivek uses, I don't get any results. If he uses the concentration I'm using, he doesn't get results.
Yep.
So I'm trying to expand that a little bit, and I'm assuming that the field, because of the field interaction, depending upon where you are in the world, or in the universe for that matter, they're going to be a little bit different every place you go. So we may have places where the capacitors won't do any good. You don't need them. There may be places where the capacitors are required. We don't quite know yet. We're still learning. We're still gathering information on this, but there is a purpose for the capacitors. As I say, my understanding is incomplete, but when it was brought up, the basic explanation was they're a stabilizer. for the device. And they help stabilize the energy. Go ahead, Dave.
I call bullshit on that, Junko.
Why?
And I've got proof in this room, because Eduardo's here and he built a unit and he plugged it in here in the south of the equator, and then he's taking it back. Where are you, Eduardo?
I am in North Carolina.
And he plugged it in and it works there. So
I'm not saying that it won't work, Dave. I'm looking at the very subtle, very finicky little bits that are involved in this. And yes,
right.
Have a field interaction regardless of where he is. Is it as strong as it was in Peru? Is it stronger than it was in Peru? But when you tested it in Peru, it was only plugged in for a few minutes. So we don't have data that way. But when we're dealing with making GANs, it's been long enough now that we do have data where, depending upon where you are, your process is going to be a little bit different.
Okay. So let's go back to Eduardo and just have a little chat with him. And you plugged your machine in that you made in Peru, which is south of the equator. You're now in North Carolina, Eduardo. What do you get? What's going on?
I have a question about this, because yes, I have here my machine. It's connected to the grid. Now already that is connected with a small fan, about 18 watts. Everything works fine, but how do I know that it's really working? Because somehow it looks like a complicated cable extension, you know.
The best way to do that is simply trust it, plug it in, plug it into your wall, plug in a load. You need somewhere around somewhere between 250 and 500 watts for the first little while. And we do recommend conditioning it gently, starting with no load and a very light load, then slowly adding the load. It's not required. You can do it. You can just plug 250 watts into it and let it run. We do this so that the people learn to be gentle, and start, they get introduced to the plasma energy, the field of plasma energy very gently. But if you're familiar with it, if you already have lived in that field of energy, then I don't think that nearly as important. So what I would do, depending upon what kind of power meter, your utility meter, is it the ones with the little spinning disc, or is it just digital numbers?
No, I have several different meters. And now on the machine... Get rid of those. Throw those away. They're useless. They will not give you any information. This one you mean?
Take it off the system.
This one you mean?
Yes.
Okay.
They will not tell you what's going on, and I'll explain in a minute. If you've got the old style utility meter out on the wall, that's got the spinning disc on it, you can plug get a 500 watt load, plug it into your wall, go out, see how fast that disc is spinning.
Yeah.
Come back in, plug in your Magrav unit, and go back out and see if this disc changes. Okay. Your true results are going to be seen over time.
Yeah.
Okay. If you put a meter, mine's in the shop. If you put like a watt meter on either side of this thing, you're gonna not read anything, because you can't measure plasma.
Yeah.
Okay? You're not outputting electricity, you're outputting plasma. The meter is measuring electricity. So you're not measuring what the device is doing. You're actually putting something in the way of the plasma. You're creating a source of failure when you plug those meters in. Okay, not only failure in your thinking, but failure in the actual plasma transfer.
Mm-hmm.
When you get the benefit, you don't have the meters on, you've got a load, you got your Magrav plugged into the wall, the device is putting plasma back into your wall, which is migrating through all of your wiring. Anything you've got plugged into your house, it's going to see it, and it's going to add a little bit of power to it, a little bit of the plasma energy to it. So that device is going to use a little bit less electricity, which will be shown in your meter. in your power meter, your utility meter. So use your utility meter. Mr. Kesh came out the last week and said the only data we accept at the foundation is a utility meter reading over time. Nothing else.
Mhm.
Everybody that I know that doesn't understand how the system works, they all plug meters in and goes, yeah, I got 10 watts in, 10 watts out. It's a piece of junk. They have no idea what the thing's outputting because you can't measure it. All you can do is follow the effects of it. And that's on your utility meter.
So, and the utility meter, it's actually trustable because it's far away from the Magrav. And
We gotta get a,
I mean,
Well, the point is you've got a whole bunch of electrical devices between your Magrav and your power meter. Each one of those devices is going to be reducing its electricity requirement because it's getting a little bit of plasma energy. So if you've got a 500 watt device between your Magrav and the power meter and you're feeding it the equivalent of 100 watts of Magrav energy, it's only going to read 400 watts on your power meter.
even if it's not connected directly to the Magrav.
If it's plugged into your wall, it is connected directly to the Magrav. What's on the output side of the Magrav is only a trigger to start the plasma flow. Your primary benefit from the unit is going back into your wall. Being reflected back into your house to help feed your devices.
Yeah, I understand.
Okay, it's not like a generator. It's not like you plug it in and you plug a bunch of stuff in and whatever you plug in is free. No, that's not how it works.
Yeah.
You plug it into your wall, you plug a load in. What else is plugged into your house is getting the benefit of the Magrav. People just, a lot of people really don't understand this. Vivek, go ahead.
Yeah, Eduardo, what sort of a meter do you have in your house? Is it the spinning disc type or is it the digital type?
I think it's a spinning disc.
Perfect.
Spinning disc.
Those are the easiest ones to see the benefit. Because it's right there in your face. When you plug something, there's a couple of videos on the golden age of Gans where the fella he's done that test. He's filmed his meter and it's spinning like crazy, and he goes and plugs in his system and meter slows right down with the same load. This is a way you can see right off the bat how this system is working. Another way, if you have a digital meter, which it's really hard to do this because you have to stand there for 20 minutes and watch the numbers and count how long it takes for a number to change. If you don't have that kind of meter, or you don't have the ability to go and dig into your meter, like you're living in an apartment building, you take an ohm meter and measure the resistance from the live side input to the live side output. Okay? It should measure millions of ohms, mega ohms. Should be very, very high resistance. If you have very high, hang on, Dave. If you hang on. If you have very high resistance and whatever you plug into the device still lights up, you know your system is working. Okay? And all you have to do is just trust it and let it run.
Yeah.
That's one way you can tell right off the bat. It's not really going to tell you anything other than a yes or no. But as soon as you have the yes, then you have the confidence of just, okay, put the load on it, let it go. We'll see what happens in 2 months. Because that's the only way you can actually test these things.
Yeah.
Dave, go ahead.
Well, yeah, John Carl, that's why I tried to interrupt you, is because Roosevelt and Carlos Flores, our engineers here in Tarapoto, showed us how to do that, and they showed us very clearly how to do that. And we got mega ohms.
Yep.
We got, I don't know how many, in fact, they were uncountable. So therefore we got a working system. And
Yes.
that's one thing we didn't do with Eduardo's system, was double check it with Roosevelt and Carlos Flores. But I'm confident that the system that Eduardo and Wan Chang, the Chinese guy, followed while they were here, and they were plugging in the machines here, they were working. They were working pretty good.
Okay, a little more data about this. If you have very low resistance, what you have is a matter state to matter state connection. You've got a flaw in your nano-coating where copper is touching copper, okay?
I can measure it right now.
If you've got mid-range resistance, kilo-ohms or tens of kilo-ohms, k-ohms, then you've simply got an insufficient nano-coating. You need to redo your nano-coating, take a little more time with it, use a little stronger caustic. There's a number of different things you can do. But on a properly made system, when you measure that live side input, live side output, so you're measuring through the coils themselves,
I'm getting now between 20.
massively high resistance. Sorry, Eduardo?
Well, I can tell you that I was so strict on Eduardo's nano-coating that when it came out on the third day, he had perfection.
Good.
And I was that strict with it, you know.
Good.
And then we dunked in the Gans, the 25% water mix with 75% water. And I dunked it, and then we put them up to dry. We knew we had very good bobbins for Eduardo and Wang Chan.
Yeah.
You know?
Once you understand a few little bits about how this functions, it's pretty easy to make a system that you're confident is going to work properly. But if you don't understand matter state to matter state or nano connections, nano-coating connections, or the purpose of the nano-coat, you're just winding wire and you're plugging it into the wall and hoping it doesn't spark. You need to understand why you're doing these things. And the nano-coating is, if it's done properly, a super insulator for electricity.
Yeah.
If you know Ohm's law, voltage over resistance times amperage, okay? Those are the three elements of the equation. If you want voltage, it's resistance times amperage. If you want amperage, it's voltage divided by resistance. So if we look at that, voltage divided by resistance equals amperage. If you've got a 110 volt system and you've got 1,000,000 ohms of resistance, you can't have 500 watts. You can't have 5 amps going through this system because the resistance will not allow that current flow.
Yeah.
So if a 5 amp device, a 500 watt device still functions, it's not running on electricity because it's mathematically impossible for it to pass that kind of current to run it on electricity. This is why that measurement is so important.
I just measured now with 2 different meters, and both of them gave me above 30 mega ohms.
Perfect. You've got excellent nano-coating. You've got a very well built system. Plug it in, put a 200, 250 watt load on it, and just let it run.
I only have a question about the connection of capacitor. What I have done here, the inside pin is connected to the neutral, and the coil is connected to the live wire. Is it correct, like this?
Is that right, Vivek? I think that was backwards, isn't it?
Because
you're muted, Viv.
Vivek,
you're muted. We can't hear you. You're talking to yourself.
I said, let me think. Hang on.
Okay. In the drawings, they don't really detail that, and I'm not certain which is which.
Yeah.
Now, the way I see the connections, you want the coil to be the source of, to be attached to where the plasma energy is coming from, and that coil puts it into the pin to continue on its way. That's just the way, with the new coils or with the new coil systems, the modular plug is built right into the coils. So on the output, this would be the output wire of one coil. You plug in the input wire of the next coil. If you look at the capacitors the same way, I think you'd be on the right track.
Eduardo, you're correct. The spring, the coils on the outside, positive. The pin on the inside, negative.
Okay.
Yeah, correct.
Okay, yeah, because people are using positive and negative, they're using in and out. I wish everybody would just use input output rather than positive negative, because it's so confusing when you try to convert.
Yeah.
And it's not positive and negative. I mean, the way we understand that, those two polarities to be, it is an input and an output, which is not actually true, because both are input and output, because you got energy going both directions at the same time.
Right. Just for simplicity's sake, the plus, which is the output, would be to the live wire, and the negative, which is the input, will be to the neutral.
Okay.
Yeah. And then on the load side, it doesn't matter. It's both of them are live.
Okay. All right. So that was a massive amount of information all at once.
And just a second, I'm making a drawing. I want to be sure what I'm doing.
If you want, you can bring up a whiteboard and draw it right on the whiteboard.
The way I connect the capacitor is like this.
Yep, that's scheme 4, isn't it, Vivek?
No, it's not.
In the blueprints,
How he draws.
they also show some possibility to put capacitor here.
Yeah.
That doesn't make so much sense for me.
Okay. Yeah, there's in the blueprints, the old pack of blueprints, there's 4 possible schemes that we could put the capacitors on. And I think it's either 3 or 4 was the ones that most people are using.
It's actually number 4.
Okay.
And what I was describing just now is schema 4. What you do on number 4, if you look at the original blueprint, I don't know why I can't bring it up on my system. It's misbehaving, but I'll describe it. If you look at configuration number 4, on the load side, exactly, you see those capacitors that are connected between the live wires. The ones that are going vertically, the one that Eduardo is showing, that is on the load side. So your output of the topmost coil comes into the input of the capacitors on the load side. Output of the load side goes to the live of the power strip on the load.
Right, that's the feedback loop that we were talking about earlier.
Yeah, but if you do it without the feedback loop, it's still live in, live out. On the grid side, it is live on the output side and neutral on the input side. So that's the only capacitor which sees neutral.
Okay.
Yeah.
All right, we'll have to get somebody to draw that up and make it a little more clear, because you know, I know what you're talking about, and I still have a hard time picturing it.
Well, I can send you the that blueprint right now if you want. Then you can.
Okay.
Okay. I'll send it to you on Skype.
Yeah. Okay. Anybody else have any ideas? Don, you're quiet. Usually you're like talking about this stuff, so.
Yeah, I just got the final thought on it. I'm not ruling it 100% that I don't need capacitor. The only reason I see this thing working because it's been conditioned it's been running for about the 3rd month now. So I still may need them for the new ones. I made new steps, like 11 reactor steps. I'm gonna finish completing them, assembling them. And I'm going to try it. I'm going to try plugging in 4 in my house and see what it does to the meter. Like you're suggesting, that's what I'm going to do. And just put some light loads on it. I'm not going to go crazy with it. I'm just plug in a fan on the load and an LED light on the upstream, you know, and just do like what you're suggesting a while back. But I always make an idea to plug my air conditioning in. Necessary. Just plug it in on the leave it, plug in anywhere in the house.
Yeah.
You know?
Yeah. You brought up a point that a lot of people have had trouble with, and that is they think they're conditioning the unit. No, the unit is already conditioned. It's ready to go. You're conditioning your house, and the device is in your house to accept plasma energy.
That's right. And it's basically a nano-coater.
Yeah, it's a plasma source, and the plasma nano-coats the wiring in your house to allow more plasma to flow. That's what the conditioning process is. You're not conditioning the device. You're not training the device to your house. You're training your house to the device.
Exactly. And then you can eventually unplug them all and give them to someone else or sell them or whatever you want with that. That's the idea.
That's the concept. We've had one report so far that's what they did, and their house continued to operate just like the Magrav was attached to it. I'm expecting by the end of the summer we should have hundreds and hundreds more of those, because their home conditioning process will be done, and more people are gonna say, yeah, this is cool, here, you take it home and you try it, and then they realize their meter is still not spinning.
John, could you accept the power transfer on Skype?
Oh, sorry.
There we go.
Okay, that's not the brand new one. That's the couple of steps back, right?
Yep, but that is the one that Eduardo was showing on screen just now.
Right. Okay.
So you will be able to find configuration number 4, 3, 2, and 1 there.
All right. Okay, Dave. So we've gone over your system, modular setup. Assemble it first, then nano-coat it. That way, you're not messing with the coating. Because if you scratch it, if you dent it, if you crack it, you're going to have problems.
Well, Liliana's here now, and one of the most beautiful girls in Peru is, can you make, ¿se puede hacer esto, Liliana? ¿Se puede hacer? See, so what we've got is a 21-year-old girl who's going to make these and mass produce them. And we haven't got a problem with that. Yep. So, John Carl, Max, Vivek, we can make these and mass produce them. And that's as simple as that, because when we insert the top into the bottom, or the bottom into the top, whichever you want to call them, what we can do is we can put the paper on these, and this is the problem we've always had over the time, is putting the paper on that. Now, if you look at that, that is basically the guts of the mass production of these things. And we spent time, you have to make one of these with one of these. Now look at that a little bit closer. That is a 9 wrap around two coils of wire, 14 gauge.
Yeah, it's not. It's
that is
for clarity for the folks out there. That's one coil. It's wrapped around 2 straight pieces of wire. So one end of that coil can fit 2 pieces of wire. The other end only fits 1.
Right, and therefore, when you come to this one here, you get 1 wrap. And then when you come to this sector here, which can be nano-coated together, because then don't forget the other just sits on the end here, which I've got here. Mm-hmm. Actually, I need that bit there, and oops, and then that bit there.
Yeah.
But what we're getting is basically a mass-produced unit that can be nano-coated, and then when you nano-coat these copper coils and this sector here, so in other words, that goes in the pot and that goes in the pot, you stick it all together, you pull it out, and you stop that problem that Keshe Foundation Germany have got, Philippines have got, and Mexico have got. You basically don't crunch your nano coating when you join these pieces together. Does that make sense, John?
That's exactly right. And you can, if you look at your system, any connection you make within the system after the nano coating, if you have it set up with these little wire coil plugs, you're going to reduce an area where you can possibly introduce a flaw in your nano coating and a matter-to-matter connection. And we know it works. We're using it in the factory. A number of people have done it this way, and they do work very, very well.
Okay.
So an hour, Dave. Is there anything else you wanna bring up?
No, I mean, I'm very excited about our findings today. We found it by accident. The reason why we found it is because we didn't put the papers on. And that's when we went, oh my God, we've got one system that fits like a glove into another system once you put the papers on it. So we were very happy about that.
All right. Oh, go ahead, Eduardo.
I have a question about this. When you put the paper on this, you should find a way to block the paper, because otherwise when you go to the second one, the first one will unwrap. Is it correct?
Hey, we didn't say it was easy. All we said is that you can do it. Everybody's going to have to find their own system. What I was doing initially was I was making them individual pieces, and because we now have that plug system, you can make them. You know, it's you're not twisting the wires, so you're not going to mash the nano coating when you plug these in. So you can still make them individually. And what I was doing was I would wrap the paper in such a way that when I go to put the center core into the coil, I actually have to turn it like putting a nut and bolt together. And that way it squeezes that paper down really, really tight and makes a very, very solid capacitor. And then once that's done, you line everything up, plug it all together, and assemble it. This is the idea of having those plugs, is to be able to make it more modular. Dave's idea of putting the three together and nano-coating that and then winding your capacitors, certainly, by all means. If you can hold the two of them together while you're winding the third one and then hold all three together and get them assembled.
Can I have some sort of tape to some insulating tape, for example? I have here this.
I would avoid it. I would think that it's going to add a problem in with the system, because at that point where the tape is, when you put it together, you don't have connection of the Gans material with the nano-coated coils.
I see.
And it's that it seems like a matter state connection, but it's a plasma connection between the matter plasma, the Gans, and that nano-coating material, which is when you have those in very close proximity, it's a very, very efficient energy transfer.
Mm-hmm.
I've got something else I can add. I'm finding that I did a test with the coil spring I had laying around, and I cold caustic this spring, and it took me 2 days to do it, and I showed John the other day, and he looked at it. He said, "That took me 2 days. What do you think of that?" He said, "Well, you look like you spray painted with a glossy finish." And so that's a different kind of nano coating. And I find when I was really rough with it, I was trying to see if it comes off. It doesn't. It's a different finish than the one you steam coated.
Yep. There's a new process that they're working on in the factory. I haven't got the details on it yet, but it apparently makes an amazingly strong, amazingly powerful nano coating. When I have the information, when I understand what they're doing and I understand why, then I'll bring it out and I'll let everybody know what's going on.
Well, my point was you could be rough with this. You can make these capacitors and not worry about it falling off or breaking or fitting them in together. Because I was really rough with it, and it wouldn't come off. I said, "What is that I've seen?"
Yeah. If you do your nano coating gently, slowly, gently, don't try to go fast.
Yeah.
It's everything that you take your time and you put a little love in works better. than something that you just slap together and do it quick. We know that from doing anything, baking a cake, building a house, doesn't matter what it is. If you try to go too fast, you have problems. So take your time with the coating. It should take 2 or 3 days. You know, some of the coatings, this I started with fire, and then I did the cold caustic method, and they've been baking in the baggies now for about a month and a half. And I'm in no hurry. I'm in no rush to do it, but this coating it looks like it's bulletproof. And when I do the measurements, when I do a resistance measurement, my meter doesn't even see it's connected. It's just like the wires. I'm holding the wires up in the air. There's no resistance, or infinite resistance. So take your time with your coating. Take your time with your GANs. Don't try to go fast. If you can come up with a way to go fast and not cause problems, by all means, do it.
I'm going to show you my coil. It's Nano-coating. I'm going to grab out the container.
Okay.
There it is. I just put it in yesterday.
Ooh, that looks very nice. Yeah, when they're done and dry, do a resistance measurement from the input and the output, and your meter shouldn't even turn on.
Right.
If it's done properly. There should be infinite resistance.
This is what I use is this salt container. I leave it in the window. It was cold last night. I'll take it outside today. It's going to warm up. And I got 3 of them going right now. So do it.
Very nice. Yeah, that should, there's no reason why the way you're doing it won't work. It's just that, doing the cold caustic, doing the cold vapor, like in a baggie or in a little container like that, it just takes a little bit longer. But it appears to be a much more robust coating. It's not as thick. It's not as black. It's still black, but it's shiny black. It's not a really flat black, which you get with the hot method. You get a very flat coating. But it's that hot method, that flat coating is easily damaged. You can squish it. You can crush it.
John, have you seen the microscopic testing of that kind of testing? Because I know the difference between heat and caustic soda is immense.
Yep.
So that's why here in Peru anyway, we are sticking with the caustic soda method. Have you seen anything to say to the contrary to that?
No, the photographs that I saw, the caustic method at, I think it was 5 micrometer, it looked like you're looking down on a city. Buildings and roads, and it goes off in all different directions. The heat coating was the same thing, but it looked like you were looking at the city from space. Okay, it had a very similar structure, but it was very, very fine at the same magnification. The coating that I did both. I started with the heat on my coils, and I went around both sides 3 times, let them all cool off, then I put them in the baggies and did the cold caustic method. Whether or not you're going to have the same quality of structure doing it that way, I don't know. But it appears to me that once you have the heat method, the very fine structure in your nano coating, and then you do the caustic method, you're going to grow a coarse coating underneath it. So you'll have these coarse buildings with a very fine veneer on it, which intuitively tells me that I'm going to have a little broader range of ability with the with the plasma flow through that. I'll have a higher frequency and a lower frequency able to pass through. Whether it's frequency, that's the only way I can describe it. I don't have any other words for it. But a broader bandwidth of plasma energy, because we know if you dip your nano coating in GANs, you're going to filter that bandwidth down to whatever that GANs is. And with the energy devices, I'd like to keep that as broad as possible to access as much of that infinite energy field as we can. Whether that's the way it goes, I can't say for sure. That's just how it feels to me.
Okay, and just for this recording, John Carl, I think, can we just recap on what we've got here, as I find that this is a crack, and it's a crack on what we've been struggling with now for 6 months, that we've got mass production, and I'm going to show it again, and this can go out to Kesh, Germany, Kesh, Philippines, Kesh, Mexico, Kesh, Peru, of course.
Yeah.
But we have got a mass productive that goes into there. You put your papers on there, that gets nano-coated. You put the whole thing in the bag, and that gets nano-coated. That gets nano-coated, and that gets stuffed on there. You've got a complete unit of capacitors, and the reason why we use capacitors on our complete unit, can you tell us again, John Carl, why we are using capacitors on this unit?
The best explanation that I can give, the simplest one I can give, is that it's a conditioning system to allow it to be more efficient.
Okay, thank you very much.
All right.
A great show.
Oh, go ahead, Dave. You look like you're still talking.
Sorry, this has been a great show because I've been struggling with the capacitors, not only with me, but I've been struggling with the Peruvian engineers who are extremely intelligent. Eduardo knows that. He's met them. And they've been coming back to me going, still not happy, still not happy, still not happy. But when I produced this today, I went, oh my God, I am, for the first time, I'm happy that I've produced a type of capacitor that I can use, and it resonates with me. So that's what's important here, is what resonates with you, and I hope it resonates with Germany, and I hope they get the message from this recording. So what do you think, John?
Well, I'm going to put it out there. I hope a whole bunch of people can get some benefit from this, can see where this is going, and maybe take it to the next level as well. I mean, we can't say that this is the end of capacitor technology with this. I'm sure that there's going to be other people come up, look at this system going, yeah, that's really cool. Why don't we do it this way? And that's even better, which is why we do this. This is why we do these shows.
Let's put the final word with Vivek, because Vivek, I was working on Vivek's technology 6 months ago, and let's put the final word with him, because he's seen now what we've come up with, and you know, he knows how it works. So Max, tell us what you think of what you see right now, because that's what we've come up with here in Peru.
That's a very, very elegant mounting solution. It's modular, and it allows you to very easily connect the bits together and nano-coat the thing as a whole. And even if you do need to remove it to wind the paper, you can still do that and then put the thing back together again without having to worry about damaging the nano-coating. So I'm really very happy about that. It is a very elegant solution. I'm very happy about it.
Okay, guys. I hope that helped. If you have any questions, put them in the comments underneath. Put them in the comments at the bottom. If you want to bitch and tell us it doesn't work, don't waste our time, because we already know it works. You're just going to make yourself look foolish. If you want to understand it, by all means, ask questions. That's why we're doing this. We love answering questions. We love explaining how this works, how to do it yourself. You don't have to buy a unit if you don't want to. If you don't want to learn it, go buy a unit. It doesn't really matter. But the availability of the information it's massive. We're always learning. We're always coming up with the next iteration, the next layer, solving the problems as we go. That's why we do this. That's why we collaborate, and that's why we're doing these shows. So I hope you enjoyed what we did. A little over an hour, about 70 minutes worth. And like I said, leave a comment if you like what you're seeing. If you don't like what you're seeing, don't watch.
Hey, listen, John Carl, I've got a special request.
Yes.
Now you've seen the mass production version. Please, can you draw it on a piece of paper? I know you're very good at that.
I'll work on getting something drawn up, and so you can have a hard copy of it.
Okay,
I need to make sure that the coil directions are right and the loop directions are right, because everybody, they just look at it and they just copy it without understanding what they're doing, and it drives me nuts, because you need to understand what you're doing. You can't just copy this.
Okay.
Well, you can, but you're not going to benefit if you just simply copy and don't try to learn something. So if you see a drawing and the coils look like they're backwards, is it a problem with the drawing? Is it the way they wanted it? If somebody said all of the coils have to be the same direction, which is absolutely accurate, all the coils, your layers, all 4 coils in each layer need to be the same direction. All of your connections need to be in the same direction. Everything needs to be consistent throughout the device. If you put one in that's backwards, you're going to introduce a narrow spot in your pipe, which is going to restrict the flow, and your system's not going to work that well. So think about what you're doing.
Okay, well,
that's something you need to really check.
very important.
Coils are right.
Yeah.
Okay.
Okay. Well, I've got news for you today. Is that I can tell you that Eduardo, who's in the room right now, has been here in Peru, and he's made all his systems correct. Well, we've just heard today, and you've heard this, John Carl, that Cobra and the White Dragon Society of China are interested in coming to Peru to make machines. So we need to have our act together here in Peru. So we're refining our act. Eduardo's been here. He's seen our act. He's used our act, and he's used it practically. He's got his machine working. And hopefully Eduardo can fix those 4 machines that he's got there that he tried before that weren't working. Maybe he can get those working. But we have got the White Dragon Society coming to Peru. We need to have our act together. Okay?
I'm not worried. I'm not worried. We've got it down. It's just a matter of getting the processes working for your system, because you don't have access. You're in Peru. You don't have access to some of the really cool stuff that people in Europe would have. Uh-oh.
It's Bertha from San Roque.
Ah, very nice. Okay, so I'll take that as we're done. You can go and visit and catch up with your friends.
Can I ask you another question, John?
Certainly, certainly.
I have here this is one of my old machines.
Okay.
I think the nano-coating is pretty good. And what was missing here was the Gans, because I have no clue how to make Gans. Now I know, I learned from Dave how to make Gans. And I wonder if I can put the Gans here without removing the machine from the stacker.
Well, I would take it apart. Your coils are too close together.
Are too close? You mean?
Yes. Double the distance that they're spaced.
Uh-huh.
You need a small container, something sort of like that you can put a Gans paste in.
Uh-huh.
Let the Gans dry until it's really thick. Okay, like frosting, like bread dough, and put it in a container, and that goes in the center of each one of the loops. Okay.
Also for this, I wanted to. This was my third machine.
Okay.
the first two before was not working. I was just following the blueprint, and here in the first blueprint they put 2.5 centimeter between the coils. So that's why it's so.
Okay. Okay. Also, when you mix up your GANs, you need to mix up two different mixes.
Yeah.
You want a very high CuO content for the inside loops, and a little bit less CuO content for the outside loops.
I see.
So you've got a very powerful in the center, then you've got a slightly less powerful on the smaller circle, and a again less powerful on the outside circle, because you need that gradient. You need to be able to use the GANs itself to create that plasma flow. And do it all the same, yeah, it's going to work. It's not going to work very well, but it will work. If you have that gradient in there in your GANs itself, then your system is going to be as efficient as you can do it.
So how to do these different percent of GANs in the two layers? How you cannot dip all the.
Well, no, you just set it on a like a styrofoam plate or you know a plate, and pour the GANs onto the coil.
Yeah, I see.
Right. You can do your lighter ones first.
Yeah.
Coat the whole thing with the light GANs, and then put another layer on the inside coil of a heavier GANs.
Yeah.
Because all you need a heavy, medium, light.
I see.
A little bit. It doesn't have to be massive. You don't have to go from lead to the inside to CH3 on the outside, which is right now the heaviest and lightest that we can produce easily. But you need to have a slight difference between your center, your inside coil, and your outside coil.
And the difference is just about the CuO.
You can have equal amounts of CuO, CO2, and then change your CH3. Put more CH3 in the outside coils. That's going to make a lighter GANs as well.
Okay.
There's a number of different ways to do it. I mentioned the CuO because that's of the big three of the carbon dioxide, the CH3, and the copper oxide. That's the heavy one that we work with.
Okay. And
that's the one that most people are familiar with. Dave, on his system, I think he added a little bit of silver GANs in with it. There's nothing wrong with that. You can do that. You can add a little bit of lead GANs, a little gold GANs, whatever you've got. But you want the three stages on each layer to be slightly different. The heaviest on the inside.
I see. Okay. Thank you.
Yeah, I put aluminium in mine, brass GANs, and then the silver GANs, and we're just learning that the silver GANs now is a killer of diseases. So I knew this was going to be big, and I expect more big information from this. So my silver GANs, and we've got a girl coming in 2 weeks' time. She's bringing gold. We're going to be making gold GANs. I do believe that is the icing on the cake. So.
All right. Well, let's get out of here, and Dave, you can go back to work. You got visitors. You got people coming in. Eduardo, thank you so much for coming in. Vivek, thanks for being here. Your input's always appreciated. Don, everybody else, y'all have a great day. We'll talk to y'all soon.
Thank you, everyone. Take care. Bye.
Thank you.